Welcome back, focused learners. Today we are treating your Cambridge computer science exam like a high-stakes game. And to beat the game, you need to understand the rules. We're opening up the Ultimate Examiner's Playbook, specifically targeting Syllabus 9618, Topic 3.1, Computers and Their Components. We're talking about the critical infrastructure here, guys: input, output, primary memory, and secondary storage. But listen, we are absolutely not just going to read textbook definitions to you today. There's no value in that. Instead, we are giving you a true insider's look into exactly what Cambridge examiners are hunting for when they have their red pens hovering over your papers. Let's set the stage and look at the challenge you're up against. I want you to imagine two different students taking this exact exam. First, we have Alex. Now, Alex is essentially a walking, talking textbook. Alex has memorized everything. So when the exam starts, Alex overloads his answers with raw, unfiltered computer science facts, literally listing every single technical detail about solid-state drives and magnetic platters. But here is the problem. Alex provides absolutely zero analysis. None. It's just a data dump. Then, on the other end of the spectrum, we have Sam. Sam is the classic rusher. Sam looks at the clock, completely panics, entirely misses the specific command word requirements of the question, and frantically writes down a super generic answer about random access memory that doesn't actually solve the problem presented on the page. If we put Alex and Sam's answers side by side, it is just an absolute sea of red pen marks. And the craziest part? Examiners consistently report that this specific topic is one of the most misunderstood areas across the entire board, from foundational levels all the way up to advanced. It doesn't matter if you studied syllabus codes 0417, 0478, 0983, 0984, 2210, or if you are currently tackling 9618, the strategy we are unpacking today is going to fundamentally change how you write your answers. We are going to level up your game paragraph by paragraph.
Okay, let's dive into the game plan. We've got a rigorous 4-part playbook today. 1. Core theoretical principles. 2. Procedural exam framework. 3. Mastering critical analysis. And 4. Top examiner pitfalls.
I want to hook you right away with a direct question drawn straight from the principal examiner reports. Seriously, think about this. Why do students find evaluating algorithm efficiency, particularly as it relates to hardware components, so incredibly hard? Why is this where everyone loses marks? The answer is that students, much like our guy Alex, treat hardware like primary memory and secondary storage as isolated islands of information. They memorize what RAM is, but they don't realize that the efficiency of an algorithm is deeply, intricately tied to the physical hardware it runs on. It's all connected. Think about it. If your algorithm requires massive amounts of primary memory to process data, but the physical system only has limited RAM available, what happens? It's going to start relying on virtual memory, and virtual memory uses your secondary storage, which is going to drastically slow down the execution time of that algorithm. If you can't articulate that specific cause and effect relationship on paper, you are going to miss the mark. So we are going to fix these critical knowledge gaps right now, ensuring you don't make the same mistakes Alex and Sam do. Let's move straight into Section 1. The core theoretical principles. If you're sitting there thinking that simple memorization of input devices, output devices, and memory hardware will earn you top marks, you are unfortunately setting yourself up for a massive disappointment. Examiners are looking for a much deeper, far more cohesive understanding of computer architecture. Take this exact quote straight from the syllabus guidance. It says, top-performing students exhibit connected, conceptual understanding transferable to unfamiliar contexts. That is huge. Let's think about our student Alex again. Alex can recite the dictionary definition of a barcode scanner perfectly, literally word for word. But when the exam throws a curveball and presents an unfamiliar context, let's say designing an automated inventory system for sub-zero temperature warehouse, Alex completely freezes. Why? Because Alex lacks conceptual understanding. Examiners want to see precise definitions and causal relationships applied dynamically to the scenario they give you. They want to see you connect the input device to the primary memory processing and finally to the secondary storage database updates. They do not just want you to recite isolated facts in a vacuum. So what's the secret weapon? It's making cross-topic connections. Drawing these structural lines across the entire syllabus is the absolute secret to elevating a basic, average answer into a top-tier, examiner-pleasing response. And the way top students structure these connections, the way they actually get them down on paper, is by decoding command words and using the PEAL framework. If you don't know PEAL, it stands for point, evidence, explanation, and link. All right, let's actually look at the PEAL framework in action to see how powerful it is. Let's say the command word on your exam is evaluate. An average student writes something like, solid-state drives are fast because they have no moving parts. Okay, true, but that's not PEAL. That's a basic fact. a top student uses the framework. First, they write their point. Solid-state drives provide superior data retrieval speeds for the warehouse system. Notice they included the context. Then the evidence. This is because SSDs utilize NAND flash memory rather than mechanical platters. Next comes the explanation. Consequently, the latency in retrieving thousands of inventory records is reduced from milliseconds to microseconds. And finally, the all-important link. This directly satisfies the client's requirement for real-time stock updates across the network. Boom! That is a true cross-topic connection. Look at the answers in front of you on your own past papers. Seriously, pull them out. Spot which of your answers actually follow Peel. If you take a moment to mentally scan your last homework assignment, you'll probably realize you are entirely missing the explanation and link stages. And that is exactly where the big marks live. Before we continue, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button, hit the bell icon right now.
All right, let's jump to Section 2, the procedural exam framework. Now that we deeply understand the theory behind cross-topic connections and the Peel framework, we absolutely must look at the practical application of these theories. How do you actually do this under exam pressure? We are going to reveal how algorithmic thinking and your hardware knowledge must be systematically structured on the exam page. This breaks down the 4 essential building blocks of algorithmic thinking required for Topic 3.1. Whenever you are asked to design a solution that interacts with hardware, like, say, reading data from a temperature sensor input, processing that data in primary memory, and logging it to a secondary storage database, you must use step-by-step decomposition, you must select the appropriate data structure, you must implement efficient logic, and you must design rigorous testing protocols. Our other student, Sam, the rusher, Sam completely ignores this process. Sam rushes straight into writing lines of code or describing the hardware without breaking the problem down first, which means Sam misses the command word requirements entirely. To stop rushing like Sam, you need a reliable success blueprint. This is a 5-step methodology showing exactly how top students build their answers systematically from start to finish every single time. Step 1. Deconstruct the question. Literally circle the command word. Is it describe? Is it explain? Is it evaluate? Step 2. Extract relevant data. Highlight the specific context in the prompt. Are you dealing with a mobile phone or a massive global server farm? It changes everything. Step 3. Select your analytical framework. In our case, for long answers, it's the Peel framework. Step 4. Execute with clear notation. Step 5. Present with correct formal terminology. Let's actually do a live transformation together right now. Let's look at Sam's original rushed answer for a question asking to explain the need for primary memory. Sam wrote, "The computer needs RAM to hold data so the CPU can use it. ROM is for booting." Okay, that gets maybe 1 mark out of 4. Let's apply our 5 steps in the Peel framework to fix it. We deconstruct. The command word is explain. We extract the context. We select Peel. Now let's rewrite this. First, the point. Primary memory is essential for the immediate execution of instructions by the CPU. Next, the evidence. RAM stores the currently running applications and user data, while ROM stores the essential bootstrap loader. Then the explanation. Because the CPU fetches instructions directly from primary memory, its access speed must be exceptionally high to prevent processing bottlenecks, which slower secondary storage simply cannot provide. And finally, the link. Therefore, without sufficient RAM and the initial instructions held in ROM, the system architecture cannot function. Do you see that? Do you see how those red pen marks instantly transform into green check marks? That is the sheer power of following the blueprint. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Let's move right along to Section 3, Mastering Critical Analysis.
This section focuses heavily on those higher-order assessment objectives. We are talking about evaluating alternatives and justifying recommendations. Listen to me closely. This right here is where the difference between a B grade and an A-star grade is decided. Let's look at the specific evaluation metrics examiners are looking for when you are assessing the quality of a given algorithm or a hardware approach. You must systematically analyze time complexity, space complexity, edge cases, and the effect on overall performance. Let's do an interactive workshop right now. I call this Challenge 1, the data scan. Imagine a complex data table pops up on your exam screen. It's comparing an optical disk to a solid-state drive for archiving massive, long-term enterprise databases. If you were given exactly 60 seconds on the clock, what data points are you going to extract? Are you just looking at the cost per gigabyte? Are you only looking at the data transfer rate? If you only analyze the speed of the drives, you fundamentally fail the critical analysis. Why? Because for a long-term archive, longevity and cost per gigabyte are the critical edge cases and performance metrics. You must scan that data and recognize that while the SSD absolutely wins on time complexity and speed, the optical disk might actually win on long-term space and cost metrics for cold archival storage. That's how you evaluate.
Now let's contrast how to properly execute a comparative analysis. When a command word explicitly asks you to compare, highlighting both the similarities and the differences and backing them up with concrete evidence is an absolute non-negotiable requirement. This brings us to challenge 2, find the flaw. I am going to read a deeply flawed sample paragraph, and I want you to mentally identify the sentence that is losing marks. Ready? Here it is. Both RAM and magnetic hard drives store data. RAM is volatile, but hard drives are non-volatile. RAM is faster. Okay, time's up. Did you spot the flaw? The examiner commentary on an answer like this would be absolutely brutal. The flaw is the complete lack of comparative connectives, the total lack of concrete evidence, and the failure to draw any sort of conclusion about relative importance. It's just a list of facts. Here's how a perfect Peel paragraph comparing these two components should actually sound. Listen to the difference. A key similarity between RAM and magnetic hard drives is that both hold binary data essential for system operation. However, a critical difference lies in their volatility and access methods. Whereas RAM provides temporary, microsecond-level direct access for the CPU, magnetic drives offer permanent, millisecond-level sequential access. Ultimately, this means RAM is prioritized for current task execution speed, while magnetic drives are optimized for long-term high-capacity data retention. Think about challenge 3, speed writing. If you had 30 seconds to write a paragraph, you need to be defaulting to that comparative structure every single time. That is how you master critical analysis and scoop up all those available marks.
Finally, let's look at section 4, top examiner pitfalls.
We are entering the final phase of our playbook. I'm going to share some specific, dire warnings straight from the desks of Cambridge principal examiners. If you want that progress bar on your mark potential reaching a full 100%, you have to avoid these traps. There are exactly 3 critical mistakes that consistently derail students year after year on this specific hardware and components topic. Let's unveil them right now so you can safeguard your grade. All right, here are the top 3 mistakes. Number 1, answers are too vague and lack technical detail. Saying a monitor shows the output is incredibly vague. You won't get a mark for that at this level. Saying a capacitive touchscreen utilizes the electrical properties of the human body to change the electrostatic field is the exact technical detail examiners are hunting for. Number 2, forgetting boundary conditions and edge cases. When you are testing hardware inputs, what happens if the sensor receives a value of exactly 0? What if it receives a negative number? You must state these edge cases explicitly in your testing strategies. Number 3, answers are not specific to the question's context. This is the biggest one. If the exam question is about designing a system for a self-driving car, and your answer talks about using a standard desktop computer mouse for user input, you have entirely ignored the context, and you will immediately bleed points. A really great memory hack for this is the acronym VEEC, Vague, Edge Cases, Context. Mentally check your answers against VEEC every single time before you move to the next page. So, the most crucial point to take away from the examiners is this massive alert. Show you're working. Method marks can save your life on these papers. This is your ultimate lifeline. The method mark strategy literally awards you points for the process, even if your final answer is completely 100% wrong. For example, if you are calculating the file size of an image to see if it will fit on a specific secondary storage device, write down every single multiplication step on the page. If you mess up the final arithmetic because you were stressed, but you clearly showed the correct methodology, the examiner will still award you method marks. Never ever leave a calculation or an algorithmic trace table blank, and never just write down the final answer without the steps that got you there. Let's wrap this up with a final system recap. To guarantee top marks and beat this game, you need to follow 3 fundamental rules. Rule 1, command word decoding. Know what you are being asked to do. Rule 2, Peel framework application. Structure your thoughts. Rule 3, maintain a time management matrix. Allocate your time based on the actual marks available so you don't end up panicking like Sam. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. I'll leave you with this one final provocative question. Are your exam answers demonstrating true cross-topic understanding, or are you just reciting vague facts in a vacuum like Alex? Challenge yourself to overhaul your study approach. Apply these frameworks and completely transform how you take on your next exam.